go telling us about decoding algorithms for good quantum LDPC codes.
Okay, yeah, thanks. And thanks for the invitation to speak here. So today I'm going to tell you about how we might decode some of these good families of quantum LDPC codes. And this talk will mainly be based on these two papers here. And I also want to thank my collaborators as well. And so the main problem that quantum error correction tries to address is that we have very noisy devices, and then we want to lower the error rate in order to do some computation. And so the idea is that we redundantly encode the information in some bigger dimensional Hilbert space so that we can actually detect the errors. And yeah, because we have this redundant encoding, then there's going to be some overheads involved. And there's going to be space overhead, which is determined by what code we're using, in particular, what code parameters we have. Like we want to have good encoding rate. And also, if the distance is scaling well, then you don't have to go to as large code sizes to achieve a certain amount of error suppression. Then there's another type of overhead, which is the time overhead of error correction. And this is just that it might take longer to do some logical operations at the, on the encoded information compared to if you just directly do it on the physical qubits. And another source of this time overhead is actually from the decoding algorithm. And like if you don't have a very good decoding algorithm, then it's possible that you might need to do many QEC rounds before being able to implement a certain a single logical operation. And so the main thing that I want to address in this talk is how can we achieve a fault-tolerant quantum computation with the lowest possible overhead. So in terms of the space overhead and the time overhead. And so the plan is that first I'll talk about, I guess, give a brief overview of these quantum LDPC codes, and in particular state one result on the space overhead when we use LDPC codes. And in the main part of the talk, I'll discuss decoders for these LDPC codes. So I'll give one algorithm that we can prove always works for certain families of these good codes. And then I'll also talk about the problem of single-shot decoding, which is how we can deal with measurement noise. And finally, I'll give some concluding remarks. Okay. So let's start off with the surface code that we all know. So we have some qubits in a two-dimensional surface, and then we have these local stabilizer checks. And the advantage of the surface code is that we can actually have geometrically local stabilizers, so they're all confined to some spatially local region. And in addition, it's been around for a long time, so we know in detail how to implement it, how to decode it, how to do logic using it. But the main disadvantage of the surface code is that it actually has quite poor code parameters. So no matter how large the surface code size is, it's going to encode one logical qubit, and the distance is only scaling as the square root of the number of qubits. So that's not super great. And that means that it's going to have a high overhead for fault tolerance. Like you might need a ratio of like 100 to 1 or 1,000 to 1 physical qubits per logical qubit. And so then we can ask, like, can we do better? But then if you want to remain in 2 dimensions, the answer is going to be no, because you run into this Bravi-Pulin-Terhal bound saying that KT squared is order n for 2 dimensions. And the surface code is already saturating this bound. So then we might want to relax the condition on geometric locality, and that allows us to define the larger class of quantum LDPC codes, low-density parity-check codes, where now we just only require the stabilizers to be constant weight, and that's advantageous because the low-weight checks are going to be easier to measure than like a very high-weight check. And it's also important for fault tolerance because you don't want one error to spread to many other errors that are involved in that same check, which could happen when you're measuring the stabilizers. And so now that we have this slightly larger class of codes, then we can again ask, like, what are the best possible parameters for LDPC codes? And I guess, yeah, maybe we know the answer to that already. And but yeah, I guess this is the some points in the history of the development of LDPC codes that Louis covered very well yesterday. But let me just highlight that, I guess, after the surface code, we have these hypergraph product constructions, and kind of using the language of algebraic topology that was really useful for developing these codes later on that have better and better parameters. And it was in late 2021 that Panteleev and Caltech prove the existence of these good quantum LDPC codes with linearly scaling dimension and distance. And these codes, I guess, are based on the lifted product or balanced product construction, along with some robust classical codes. So after this construction, there were some alternatives proposed in the form of quantum Tanner codes and these DHLV codes that also achieve the same parameter scaling. And so for this talk, I'll mostly be focusing on the quantum Tanner codes because they were a bit easier to analyze. But actually, the results can also be applied to the expander lifted product codes because actually these two types of codes are related by some local transformations. Okay, so because now we have all of these quantum LDPC codes with good parameters, then we can actually start to apply this result by Gottesman that says that if you have a code with constant encoding rate and also polynomially scaling distance, then it actually allows you to do quantum error correction with constant space overhead. So if we look at all of these codes here, of course, all of these good constructions satisfied, but I guess also this hypergraph product code is sufficient to apply that theorem. But this this theorem also comes with a few conditions that needs to be thought about. And one of them is that we need to implement long-range interactions. And yeah, because if we want to remain spatially local, then again we're running into this probably pull inter Hall bound. And so I guess last year there was a lot of interesting proposals on how we might deal with this issue. And Chris yesterday talked about this scheme of hierarchical codes if you have some architecture that only has geometrically local couplings. But then, if you have a better scenario with all-to-all connectivity, such as when you can move atoms around, then there's also proposals for how you might measure stabilizers in these LDPC codes. And also, if you can have a limited number of long-range connections, then that was also described in yesterday's talk by Ted. Okay, so this is just to say that the spatial localities, like long-range interactions, is not inherently does not preclude, I guess, the implementation of these LDPC codes. And one other condition that is needed to use this theorem is actually that we need to have an efficient decoder if we're not assuming that classical computation is free. And so this kind of brings me to the next part of my talk, which is how we can decode certain families of LDPC codes. So, okay, so in the setup of a decoding problem, we assume that we have some encoded state and we're doing computation on it, or we're just keeping it as storage. But then some unknown error is applied to the state. And so what we do is we measure the stabilizer generators, and that allows us to extract the syndrome. And the syndrome is just the classical bit string saying which stabilizer is anti-commuted with the error. And we input that into a classical algorithm, which will then output a correction f hat. And we say that the decoder succeeds if E plus f hat will take you back to the original code state. In other words, if it is a stabilizer. So the general problem of decoding, I mean, it's an important one to, it's important to have an efficient decoder because you actually have to decode faster than errors accumulate on your device, or else you're going to run into this backlog problem where, you're trying to decode it and then more errors have accumulated, and the next round there's more errors, and it will just take longer and longer to do your computation. And you can't leave all of the decoding until the end because you actually need to know exactly what polyframe you're in order to implement certain logical operations, such as non-Clifford gates. And so the general problem is actually MP or sharp P complete to decode like a arbitrary stabilizer code. So we're probably not going to have a super general algorithm to do it, but then we can still consider like specific codes. And if it's a code that we want to implement in practice, of course, then we will need a efficient decoding algorithm. And right, so there's two settings for decoding that we can consider. The first is for adversarial noise. And in this setting, like we're kind of dealing with a worst case scenario. Someone hands you like an error that is chosen adversarially, and you have to be able to decode that if the error is sufficiently small weight, meaning up to some constant fraction of the distance. And then in the stochastic noise setting, that's maybe a more realistic scenario where there's some random process of errors occurring on your device, and you have to be able to decode with high probability. So in general, these two settings are not comparable with each other, because in the stochastic case, like you don't have to decode every single possible error, just like the ones that will most commonly occur. And in the adversarial setting, you might not have to decode errors of very high weight that would be typical in the stochastic case. And so these two settings are, so they're not comparable with each other. But if we have a code of linear distance, then actually the ability to decode in the adversarial case will automatically imply the ability to decode in the stochastic case. Okay. So now let me get into more of the specifics of the code that we're working with. So that's going to be these quantum Tanner codes developed by Leverrier and Zemmour. And so how the construction works is that it's based on this left-right Cayley complex, which is just some two-dimensional expanding object. And because it's a two-dimensional object, it's going to have vertices, edges, and faces. And the faces for this complex are going to be squares. Okay, so then we're going to place the qubits on the squares of this complex. And we're going to place checks, x-type and z-type stabilizer checks on the vertices of the complex. So here I've drawn like a portion of this complex, and we're placing the qubits on the faces here. And let's say this is a z-type vertex, so we're going to have a bunch of z-type stabilizers associated with this vertex. And all of the z-type checks are going to have support on some subset of these qubits. So I didn't specify exactly how that is done, but it's going to be determined by some local classical code. And if that code is chosen to have some robustness conditions, and also the left-right Cayley complex is sufficiently expanding, then it was shown that this code will have parameters like a linearly scaling dimension and linearly scaling distance. So it gives asymptotically good code. Okay. So now let's discuss how we might decode such a code. So again, here I've drawn a portion of this complex. And let's say that, so it's a CSS code, so let's just consider decoding X errors. And let's say the highlighted faces are where the errors have occurred. And the way that the local checks are chosen, so the classical code has to be chosen appropriately, but it's basically going to require that if we want to satisfy all the checks on a particular vertex, then the error has to have high enough weight around that vertex. Okay, so if this is the entire error region, then technically it's possible for all of the checks at this particular vertex to be satisfied. So you don't have any syndrome of the error at this particular vertex. It's possible, like kind of in the worst case, you might not detect it. Okay, so all of the checks in the kind of like the bulk of this error region could be satisfied, like in the worst case. But if we look at the boundary of this error region, then there's actually going to be a lot of violations, because let's say around this vertex, there's only one qubit that's corrupted, and the local code is not going to be happy with that. So you detect the syndrome at all of these boundary locations. And also because it's some kind of an expanding object, then the boundary is going to be very large. So the idea for the decoder is that maybe we can make some flips around the boundary of this error region, and that would result in more satisfied checks than before we did the flip. So we don't see where the error is, but we can just use this kind of cost function in order to decrease this number of satisfied checks. Okay. So when we do that, so it will result in more satisfied checks, and that will result in reducing the error region. And when we iteratively do that, then it kind of reduces the region slowly until it eventually goes to 0. Okay, so that is kind of the intuition. But now let me say like a bit more specifically how the decoder works. So again, we're decoding the X-type error. Then around every single Z-type vertex, we're going to compute a candidate correction, epsilon v. So epsilon v is chosen to be a minimum weight correction, meaning that it's the minimum weight thing that if we were to flip these qubits, so apply an x operator to these qubits, then that would result in all of the checks at this vertex being satisfied. Okay. So we compute this epsilon v for every single z-type vertex, and then we just compute the potential function by summing the weights of all of the epsilon v's. So for example, this might be one configuration of epsilon v, and then maybe for like another vertex, we would have this epsilon v prime, and we sum it up, and it would give a potential function of 4, because this middle qubit here is counted twice. Okay. So in the main part of the algorithm, we're going to be flipping qubits in some local regions in order to decrease this potential function. In the example that I've illustrated, we could flip this middle qubit, and that would help satisfy the checks of this vertex and also this vertex. So that would end up decreasing the potential function by 2. So we would want to make that particular flip. Okay, and we just keep doing this process until we reach 0 potential, in which case all of the checks will actually be satisfied, and we're back into the code space. Okay, so that is the algorithm. And the main theorem that we prove here is that there is a family of quantum Tanner codes with these asymptotically good parameters, such that this decoder that I call this potential-based decoder actually works. In other words, if the errors have sufficiently small weight, then it can get you back into the code space, and it will be the original state that you started with. And furthermore, the time complexity is going to be linear. The way that this is proved is essentially just, well, it's kind of using this intuition that I've described here, where you can always make, like, the most difficult part of the proof is actually showing that it doesn't get stuck, that you can always do some flip to decrease the potential. And the intuition for that is kind of illustrated here, where you make flips around the boundary. Okay. Right. And so I guess I can make one remark, is that this is kind of like the first decoder that can correct adversarial errors of up to linear weight. And the reason for that is kind of before we didn't have any linear distance codes. So adversarially, you can only correct up to half the distance. And so the previous best adversarial decoder was this one by Evra, Kaufman, and Zamor that can go up to root n log n. It's based on a different code construction. Okay, so this theorem is kind of talking about the adversarial scenario, because we're saying if the error has sufficiently small weight. But we can, using this result, we can immediately also get the stochastic setting. And let me say exactly how that works. So we can consider some just a simple error model where it's, let's say it's IID errors, where each qubit is corrupted with some small probability. Then the decoder is going to succeed with probability exponentially close to 1. And so it's kind of a 2-line proof. So by the main theorem, the decoder is succeeding if the error weight is sufficiently small. And the distribution of the error weight is just some binomial distribution, and it's exponentially unlikely for it to be greater than this p star times n. Okay, so now let me get into the single-shot decoding part. And I guess the main question here is, like, what happens if the syndrome is corrupted? Because you're running a quantum circuit to extract the syndrome, and you might end up with the incorrect syndrome bits. And there's like a lot of standard procedures that can deal with this, which is that you could repeat measurement rounds. If one measurement round is unreliable, you just repeat until you get some consistent results. But this will incur like a large time overhead, because you have to repeat a number of times equal to the distance, or the distance squared. Another approach is that you could prepare some more complicated ancilla state and use that ancilla state to do the measurement, which would result in a more robust measurement. However, here you have to have a space overhead of preparing the ancilla state, and you transfer a lot of the time complexity from a repeated measurement round into like preparing the ancilla state itself. So these are like generic approaches that could work for any code and any decoder. But it turns out that there's an alternative approach proposed by Bonbin, which is called single-shot quantum error correction. And for single-shot quantum error correction, it means that sometimes we can make progress in decoding even with the noisy syndrome data. So in particular, like the decoder takes in this noisy syndrome data and still outputs a reasonable correction. So it might not take you back exactly into the code space, but it could leave some very small residual error that is manageable. And in this single-shot setting, one can again consider either adversarial or stochastic noise, which are like not comparable unless you're dealing with the case of linear distance, where the adversarial case implies the stochastic case. Okay, so single-shot decoders actually exist for a few types of codes already. And we know that for certain types of topological codes, such as 4D toric code, 3D subsystem toric code, or 3D gauge color code, they will have the single-shot property. And the idea here is that there's some redundancies in the check operators. So in this picture here is of the 3D subsystem toric code where the syndromes have to form closed loops. So if you do your stabilizer checks and they're not forming closed loops, then you know that some syndrome error has occurred. So you can like correct the syndrome error first and then correct the data errors. Okay, and for topological codes, a lot of the times it was considered in the stochastic setting. But there's another type of code, like these quantum expander codes, that were also proven to be single-shot. And here, like, there's not necessarily any redundancies in the checks, but the single-shot property is coming from the expansion of the code. And this is kind of also the property that we're using to prove single-shot in these good quantum LDPC codes. And for these quantum expander codes, it was proven in both the stochastic and the adversarial scenarios. And one other result was by Campbell, which is quite interesting. That can show that actually, like any stabilizer code can be made into a single-shot code if you pick the correct stabilizer generators to measure. So instead of measuring the original generators, you can take some other set, and then somehow that is more robust to measurement errors. But one problem here is that if you start with an LDPC code with low density, with low weight checks, then when you consider this other set that you actually have to measure, it could be high weight. So it would not keep this LDPC property. Okay. So I guess here I can present like a more specific definition of single shot that we use, which is that, again, we're given as input some noisy syndrome, which is coming from a data error E, but also the syndrome error D. And we want to, again, output F hat. And we say that the decoder is single shot with parameters alpha, beta. If for sufficiently low weight errors, then the residual error is going to be bounded by alpha times the initial data error size, plus beta times the weight of the syndrome error. So this subscript R here means that it's the stabilizer reduced weight, meaning that we can add any stabilizer to the thing here in order to take the least Hamming weight possible. And this is just because the errors are like really only defined up to stabilizers. Okay, so this is the definition of single shot that we use.
This is specifically for phenomenological noise?
Yeah, so in this case, we're considering phenomenological noise, but later I'll say how this might work for circuit noise as well. So, okay, let me discuss a bit about the decoder that we're using for single shot. It's a slightly different decoder that was developed by Leverrier and Zemmour, which is kind of based on this mismatch decomposition procedure. But actually, it works very similarly to this potential-based decoder that I presented previously. And the only difference is that, okay, so this is also a greedy decoder that's making local flips. And the difference is that it's using this mismatch function instead of this potential function. So for the potential function, we sum the weights of all of these candidate corrections. And for the mismatch function, we do the sum of the candidate corrections mod 2 first, and then we take the weight of that resulting vector. So I guess in this example here, the potential would be 4 because we count this qubit twice, But then for the mismatch, like there's going to be some cancellation on here, so the mismatch is actually 2. So, but actually, like in the first step of the decoding algorithm for the potential function, we could just flip this qubit, right? Like that's kind of the first step that we would do. And after you do this flip, then both cost functions would be the same, and actually they would operate in the same way. Right, so again, at every step, we're flipping qubits in local regions in order to decrease this mismatch. And instead of stopping until we reach 0 potential, we just stop when no more flips are possible. So it's possible to get stuck, it's possible to get stuck at some point in the algorithm because you might get messed up by some of these syndrome errors. And for this mismatch decomposition procedure, the algorithm could be run sequentially, in which case it would have a linear running time. Or there's also this parallel version of this decoder that has logarithmic running time. And the way that the parallel decoder works is that because we do flips in some local regions, we can just do a bunch of these flips in parallel. So this algorithm can be parallelized, and it will have a logarithmic running time. Now let me say a bit of intuition about why this decoder might be expected to be single shot. And remember before, we're saying somehow the flips can be made around the boundary of this error region because then that would result in more satisfied checks. But it turns out that because this complex is very expanding, the boundary is going to be very large. So that means that there's actually many places where we could make the correction in order to decrease this potential or mismatch function. And because of that, it's possible that your syndrome error could mess up some of these syndromes here, in which case you can't make the correction around certain parts in the boundary. But there's going to be some other portion of the boundary that's not corrupted by the syndrome, and you can actually just make the correction there. So you can still kind of decrease this error region until eventually the error region is just dominated by the syndrome noise, and that's kind of where you get stuck in the end. So that's also why that in the definition of single shot, the final residual error could depend on the initial syndrome error, because that's where you get stuck in the end. Okay, so the main theorem that we proved for single shot is that actually both the sequential and the parallel decoders are single shot. So the sequential decoder is a single shot with the parameters 0 beta, and for the parallel decoder, it's 2 to the minus k beta. And in the parallel case, technically you don't have to run it until it gets stuck, but you can just set some fixed number of iterations to run for, and it will still actually be a single shot decoder. Okay, so this theorem, again, is dealing with the adversarial scenario, just because the definition of alpha beta single shot here means that for any sufficiently small error, then it has to satisfy this property. But I can again say some things about what happens in the stochastic setting. So in the stochastic setting, let's again consider some IID model of errors. So both the data and the syndrome errors could be corrupted. And we start with some code state. The error is corrupting it, and then we decode it, and it takes you back to some other state that could be close to code space. And then we just run this procedure many times. And what we show is that if the errors have sufficiently small probability, then the quantum information can be maintained for an exponential number of rounds with high probability. And by maintaining the information, I mean that after every round, the residual error is going to be very small. One can also generalize this kind of result, where you don't necessarily have IID errors, but there could be some space or time correlation. The only requirement is that at every single round, the marginal probability of having a very large error at that round is small. Right? So this is a condition that you're going to need, or else you just have one round and it corrupts your entire data. And because this can also handle this kind of correlation, then that actually allows you to decode circuit noise as well. Because in the case of circuit noise, one component of the circuit could fail, and then that could propagate into a few data or syndrome errors. But then because we can deal with this correlation, that would just result in the threshold maybe being lowered by some constant factor. Okay, so then what that means for the overhead is that actually we can achieve constant time decoding for these quantum Tanner codes. And the way that this works is that, so we showed that the parallel decoder is a single-shot decoder, and we could take k to be a sufficiently large constant, meaning that you only run a constant amount of classical computation in between every decoding round. So during the computation, we use the previous theorem to show that the residual errors are always going to be small. And maybe at the end, then we want to actually read off the logical information. So in that case, maybe we would just measure all of the qubits in the Z basis that will allow you to perform a logical computational basis measurement. When we do that, we can actually treat all of the measurement errors as an X qubit error, like right before the measurement. And additionally, we can maybe run a more accurate decoder, for example, the sequential decoder or the log n iteration parallel decoder. And because for those decoders, like we have the parameter alpha equals 0, it doesn't depend on the initial data error. And also when we treat measurement errors as X qubit errors before the measurement, then we also assume that there's no measurement error. So basically this whole right-hand side is 0, and you're left with 0 residual error. And you actually perfectly read off the information. So the conclusion here is that we can achieve constant time overhead during the computation when we're using these quantum Tanner codes decoded with this single-shot decoder. Okay, that's kind of takes me to the end of my talk. So the summary is that we've shown, we've shown that these quantum Tanner codes can be decoded efficiently, and that these decoders also have the single-shot property. So if we combine that with Gottesman's result on constant space overhead, then we actually achieve like a constant space and constant time overhead using these quantum Tanner codes. As for the next step, like I guess one question that everyone is thinking about is how we can do logical gates using these quantum LDPC codes, because like if you just have a decoder, then that basically allows you to do quantum memory, but we also want to do operations on the code. And another question is, like kind of in the finite regime, like what are the right codes to use? And people are already starting to think about this question. For these asymptotically good codes, they come with very large constants. So as they are right now, it's probably not the code of choice, but maybe we need to come up with better constructions or find what are the good constructions to actually use in the finite regime. And finally, one of personal interest is how we can analyze these local greedy decoders in a more systematic way. Because a lot of, these like small Cephalid type algorithms are working for different types of codes, but then they're all proven in like very different ways. So it would be nice if there was some better framework for analyzing them. So yeah, I think that's basically the end of my talk. So thanks for listening.
Any questions? Can you clarify what you mean by time overhead is constant?
Yeah, so I just mean like during the computation, like we're running a constant amount of classical processing between every step, and so. Yeah. So I guess we don't know exactly how to implement this logical operations yet. But like, if at one step you can implement one logical operations, it's not like the surface code where you need to wait D rounds before you do the next logical operation. And also the classical processing is going to be constant.
But that's not a fair comparison, I think, because without the logical gadgets, it's unclear whether the parallelism of the surface code here.
Yeah. I meant for like, yeah, so we don't have the logical gates yet. Yeah, that's for sure.
Great talk. So I'm trying to still understand the importance of single-shot decoding. I can have, say, two LDPC codes. One has single-shot decoding, but it's not clear from the proofs of single-shot decoders, like what is the effective distance, right? Like seems like the effective distance of your code can be dramatically less if you do single-shot decoding. So if I have an LDPC code with smaller effective distance when I do single shot decoding, compared to another LDPC code where I don't have single shot decoding, maybe I have to do multiple measurements, but with a smaller size code, I can achieve a lower logical error rate because I'm not degrading the effective distance. So
Right.
overall, in one case, I have to decode a much bigger code to reach the desired logical error rate. In the other case, I have to decode a smaller code to reach the desired logical error rate.
Right.
It's actually better, even in absolute time terms.
Right. So yeah, I guess a lot of the results here kind of have some constants involved, which we don't know what are the comparisons between different codes in terms of the constants. But also it's if this single shot property is reducing the distance by a lot, maybe it is better to repeat multiple rounds. Maybe not single shot, right? But you do a constant number of measurements, and that will kind of boost your syndrome error rate.
So there is hope that for these LDPC codes which have single shot decoders, maybe a constant number of measurements would actually preserve the distance, or the measurements don't need to scale as the distance or something, but they will just be actually constant.
Yeah, that's possible. And also one thing you can do is you might not have to literally repeat the measurements, but you could have some small classical code on top of the measurements. And for example, in the very beginning of this here. So in when I was describing how we place the stabilizers, because there's a bunch of stabilizer checks associated with this particular vertex that all touch some subset here. So if you use some small classical code on top of that, then you would not really increase the weight of the checks because they're always going to be restricted to this particular local piece. So maybe that's also one thing that could be done.
I just want to add a comment that is, single shot is not about measuring it once. It's about measuring it constant time, or the number of times it doesn't scale with the system, right? So what you're saying, if instead of measuring once or 3 times, if this, I would all call it single shot, right?
Yeah. So, do I understand correctly that this, you didn't really talk about it explicitly, but this algorithm requires sort of expansion in the code?
Yes.
So it wouldn't work for any, let's say, code that can be embedded in D dimensions, which is therefore doesn't have any expansion period, or you don't know?
I'm not. Well, yeah. I guess it would have to depend on the specific code. So that's one of the things, right? That we don't have a systematic way to analyze these small sets of type decoders. So it's every time you get a code, you have to try to redo the proof.
But the proof that you have require certain set of certain
Yes.
coefficients, and you are not very careful about the constant, so you don't know exactly how much expansion you need.
Right. Well, we need I think actually close to the optimal. They have to. Well, okay, maybe they don't have to be close to the optimal, but they need some kind of spectral expansion in the complex.
And have you tried to implement it and play with some codes? No.
I personally have not. Yeah, because also there's a problem of these local codes that we don't really know how to find these robust local codes. They're just guaranteed to exist. So, yeah, that's also one problem.
Did I understand correctly that you prove the single shot property for the LZ algorithm, but not your algorithm you started with?
Right. So we prove it for this this Leverian-Zemmour algorithm. But actually, these two algorithms are operating in almost the same way. So I think we don't explicitly prove it in the paper, but we have one remark that was you could always just match one correction set from one algorithm to another correction set on the other algorithm.
So constants, this alpha, beta don't change.
The alpha and beta. It's possible that they might change, but yeah, we didn't work out all the details of this, but I'm fairly sure that like it would also, like the other algorithm would also be single shot.
I have a question about constant time decoding. So during suppressed error, you need a larger and larger distance. You have a more and more number of qubits, right? Apparently, so to my understanding, you're saying that the number of iteration can be constant.
Yeah.
But apparently, the input, the bit length of input bit string for the decoders, and also the output of the errors, if you present it as a bit string, this grows as you increase the distance, to my understanding.
Yeah.
So there must be some underlying assumption on the computational model, like
Yeah, because we
just input and output this string.
sure, yeah, but the model is that we assume that there's a parallel. There's like I guess you can assume that there's some maybe small machine at every single local view, and then that will just tell you like what corrections you need to do like, around that particular area in the code. So it doesn't need to know information about the rest of the code, which is why it can stay constant.
Just to assume random access memory, is it sufficient? Sorry. Is it sufficient to assume, just to assume random access memory, like array, which you can randomly access within constant time?
Well, it only needs to access the information around that particular place. It does.
You need local access.
Yeah, it's completely local. You can compute everything locally like this. Okay, I guess like this potential function is the sum of all of these things, but actually you don't need to know this like the entire potential function. You just need to know like locally, can you decrease the potential function?
I guess I have a question, which is now that we've done we've got the fuzzy propagated value proof for hypergraph particles. This exists for like the good codes. Is there a sort of like streamlined process where I give you like in the previous talk, I give you like some code for which I know how to correct adversarial errors, and then you tell me immediately I can just turn the crank because the underlying parts of the machinery are all the same, and I get out stuff that's either single shot or stochastic errors, syndrome errors, whatever the usual questions that are asked after you do.
I think it's a bit tricky because yeah, before we tried to do the proof with this potential-based decoder, but then we were running into some problems with some parts not being. Yeah, like somehow we found the analysis with the mismatch decomposition decoder was easier than the potential-based one. So yeah, before we were trying to come up with a more general framework for, like if the code or the decoder has some properties, then it automatically will imply single shot. But that proved to be a bit tricky.
If there are no more questions, let's thank Lily again. We will meet again at 3:30.